So the molecular replacement is finished. Let's take a look at the results. So first for P41, let's look at the top solution. So the important thing to look at is the translation function z-score, TFZ, which is the number of sigma above the mean that the translation function is. So the documentation says that if this number is above 8, it's definitely solved, which is nearly true. If it's 5, as it is here, it might be solved, but can't be guaranteed. I have had correct solutions with TFZs as low as 4, also with NMR models. Okay, so for P41, my best TFZ searching for a dimer is 5.5. Let's see how it was for P43. So here it's 8.3, so a much higher TFZ and into the region where we think we probably have a solution. If we have 2 dimers, it's not complete solution, but it is probably correct. Let's take a look at those coordinates. So 4.1, which is P41, and 5.1, which is P43. Okay, so for P41, it's just 2 monomers hanging in space, and for P43, this looks like it might be a biological dimer in that we have these 2 helices packing against each other and these 2 strands forming a sheet. So if this is the biological dimer, it means P43 is the correct space group, and I can make the molecular replacement search much quicker now by searching for 2 copies of this and finding those 2 in the asymmetric unit. Now, I actually happen to know that there are 2 dimers, and this is the biological dimer because I've done this molecular replacement before, and at the time I was very pleased with myself for spotting this, because finding 4 copies by individually, basically phaser at the time didn't work. So this is a way of shortcutting the solution, because the search for these 2 dimers will be very quick. Okay, so let's start the next search. We'll do a new phaser job in now P43, search 2 dimers. P43, running with the MTZ space group, and we will now use as our search model the result in P43 previously. So this is now the dimer, and we will now search for 2 of those, and we will assume the same RMSD and leave the defaults. So let's go with that, and this should now be quick. It should only take a minute to run. Let's look at the log file. So phaser does lots of things, but it does an analysis of the unit cell. So here it predicts the composition, so it agrees with the Matthews coefficient program that 2 dimers is the most likely composition. Actually, that's not based on my input, that's just based on the average solvent content. And then it does rotation functions and translation functions. And it does multiple copies, so I'm seeing quite high TFZs for searching just 1 dimer. Is this finished yet? Okay, so it's probably not productive to look at the phasor log file while the program is running because there's a lot of stuff in here. It's maybe just best to wait for it to finish. Okay, so it's found solutions, it's now refining them. Okay, this will take a moment, so I'll pause. Okay, so it's finished. The whole job only took 2 minutes, 50 seconds. The top solution has a TFZ score of 11.6, which is into the region of, yes, we believe this is definitely correct. So I believe this is a solution. Let's look at the PDB file with the map. So we can look at 6.1. This is job number 6.1, which is the job we've just run. And we will look at the MTZ file. So phasor from the model calculates phases, and then this MTZ file includes the intensities and structure factors. So Qt will now calculate a map using these intensities and phases and display it against the model. So you have to be very careful with molecular replacement that if you have a totally wrong solution, the map for it can actually look quite reasonable. So the trick, the test of whether something is correct is that it refines, and also that the map shows detail that is not present in the model. So let's look at C alphas. So I now see that's one biological dimer in the yellow and orange, and there is another one, and that looks reasonably well packed. I see that these loops are clashing, so if this is a correct solution, they're in the wrong place. But this is a good sign, because if I look here, I see that the model has the density coming out to the right, but I see density coming up for this loop. So it looks like the the density calculated from the model is already telling me how to improve the model, which means that this solution is almost certainly correct. Let's look in another place. That's an arginine. Is that complete in the model? Yes, it is. Okay. Here, for example, the model, the densities may be telling me that this tryptophan needs to be flipped over. Let's find an incomplete residue. Rotamer analysis. Okay. Methionine. Okay. Okay, so possibly this methionine extends into this bit of the density. I can't really tell actually. This bit looks like it needs to be moved. This loop looks like it's in the wrong position and needs refining, but in general I think this solution is correct. Another interesting thing to do is to look at the crystal packing. So correct solutions should have a crystal lattice that looks complete, with no gaps that extend all the way through. So let's colour by chain. Look at the ribbon. So PyMol is good for this because we can do action, generate symmetry mates within 50 angstroms. Okay, so we see what looks like a nice lattice, that there are crystal contacts in this all the way through, and if I turn 90 degrees all the way through this way, and this is just an approximate test, that this lattice looks physically plausible. So it has big solvent voids, but there is continuous crystal contacts. Okay, so I believe we have a correct solution. I normally, one thing one could do is immediately delete bits that look wrong in the density and then refine it, or do a round of refinement immediately. I think I will just do a round of refinement immediately. So we should see the R factor drop. So our structure factors we're refining against are the P43, and our PDB in is our molecular replacement solution with the 2 dimers. We'll call it RefMac1. Refinement parameters. Things won't improve very much, so 10 cycles is probably okay. We won't output hydrogens. We'll use the resolution range in the PDB. These defaults are okay at the moment. We will use NCS restraints, so we have 4 copies which should be similar to each other, so we will restrain them to be similar to each other, which helps our R-free prediction, or our R-free. So this should take a couple of minutes. Again, it's like watching a pot boiling to look at this while it's running. So it should give a whole load of errors associated with the atoms being missing because we have many incomplete residues from the model. So yeah, it's complaining about discontinuities in the structure and missing atoms. So for example, C gamma 2 of isoleucine 10 is missing in the structure and more. So you see up there, that was many more complaints, and our free R factor is, after 2 cycles, 49.5%. A random structure has an R factor of free R of 56%. Typical molecular replacement solutions can start even at 56% or 51%. But what makes them correct solutions is not that the R factor is good, it's that when you refine them, the R factor rapidly drops. So let's look at this. So in 10 cycles, our R free has gone from 49 to 49.5 to 49, which is not amazingly brilliant, but it is a small drop and suggestive that this solution is correct. So let's take a look at how that density looks. So I normally find after you've done some refinements, the scale of it looks a bit better and it's a little bit more interpretable. Okay, so it's complaining about nomenclature errors because RefMac has probably flipped things around a bit. And we can now look at our structure. Let's try to look at difference map peaks. So this will correspond to bad regions. So I'm looking at 4 sigma peaks. Okay, so here possibly this tyrosine is in the wrong place. I think there's much worse things wrong with the structure than that tyrosine. This whole loop needs to be moved into the density. This loop is, you can see it's in the wrong place. The density wants to go up through the middle here. This is a good sign. This means this residue is incomplete, so this methionine is incomplete and there's a big blob of green density where the rest of the side chain should be. So this map is telling me things that I know are present that are not present in the model. So this is definitely a correct molecular replacement solution. It just needs refining and model building into an accurate model, or rather a precise model. Okay, so I think this now marks the end of the molecular replacement step of the structure's solution, and the next part is to move into model building and refinement.